Welcome to Drone Systems and Control course. It's a lecture 38. We are going to talk about advanced drone called variable pitch quadcopter. This particular quadcopter is designed to operate even under failure, even one complete actuator failure. How you can take this quadcopter and complete the mission. What basically we meant is, can I achieve full attitude performance even if you lose one motor and propeller without yawing, and you can maneuver and land safely. That's one important aspect. Why I picked up this topic? So we talked about modeling, we talked about simulation, we talked about sensor, and we talked about control, navigation and autonomy. And we also connected with how AI really helps in intelligent control. This particular example is going to cover every aspects of the course and show you how we use this to implement and realize and validate. Right? Now let's try to understand what is variable pitch means. Traditionally, if you look at our quadcopters, whatever we are using, they have a fixed pitch. We only vary the RPM to generate the thrust force. Variable pitch quadcopters are the one where you can change the pitch angle in addition to RPM. This is more like our helicopter tail rotor, right? So you can change the pitch and you can also control the RPM. So you have a two input. You change the pitch, you can also change the thrust. You can change the RPM, you can also change the thrust. So there are two input to get the same output. Okay. So what are the benefits of a typical quadcopter? I can do flip, mid-flight flip. So if the quadcopter is flying up, I can change the pitch of the propeller so that the thrust direction can be reversed and you can fly upside down. What I am showing here is one of the work done by Jonathan Ho in MIT. They showed in a fixed condition, mounted on a fixed frame, they showed that by changing the pitch of the propeller, you can change the quadcopter to fly upside down. The direction of the thrust can be reversed, but the actuation is very important, right? Now, moment I bring in the pitch, the vibration that I am going to get from this system is going to be high. The mechanism for actuation of pitch as well as the RPM is going to be complex. That's a one disadvantage. If you look at complexity, mechanical design complexity comes into picture. The advantage is I can have a fault tolerance. I can also fly upside down when we are talking about to protect your sensors. Imagine you are flying through the tunnel and you are trying to inspect something in the top. Suddenly there is a pipe just present in top of it. You want to protect your sensor, you can flip, right? And sensor can be brought down and then you can go. Or if your sensor at the bottom, you are inspecting the quality, suddenly there is a water, you can flip up so that the sensor is protected, and you can navigate through the constrained space, right? Now, what is the advantage when we talk about actuator failure? Okay. See, complete actuator failure is a challenge in a quadcopter. If you use hexacopter or octa, you have a redundancy. With that, you can provide somehow the stability for yaw stability and you can make it land. The moment one of the motor fails, right, either you can get into yaw or spiral motion. You can land safely with the spiral motion, but you will never be able to achieve necessary attitude control if you want to continue on the mission. That is one of the bigger problem, right? So the yaw rates, if you look at, it will be something like 20 radians per second, even sometimes much higher than that. The advantage if you use a variable pitch propeller, right, I can provide a full attitude control even if one of the motor is stuck, right? I can RPM alone, I can just get it done, and propeller pitch can also be controlled independently and they can handle the actuator failure, right? So what we are going to do is, we have wanted to, now this is the background, I want to flip, I also want to provide actuator failure fault tolerancy, how am I going to do? So full attitude control even after complete actuator failure, mid-flight flipping are the requirement. Can I achieve mid-flight flipping? Not in fixed frame, I want to do it in outdoor. I am complete actuator failure, I don't want to do it in motion capture like what happens here. Can I do it in a normal environment? So these are the things, because moment you talk about normal environment, the position data which is required going to be affected significantly based on your sensor, your wind, environmental conditions going to affect it significantly. Right? Now let's look at typical quad. We want a hover equilibrium, right? So this is a typical quadcopter, T1, T2, T3, T4. These are the 4 thrusts that we are getting, right? One of the motor I just provided in brown color to indicate this T4 is under failure, right? If it's failed means I don't get the thrust, I don't get the torque, right? So the torque generated and thrust are just given here for your understanding. If you recap, it's what we use to derive. So if I am talking about a hover condition, what is my condition? T1 plus T3 should be taking care of my weight, right? The remaining torque. Suppose let's say I am going to switch off this particular motor, right? Then T1 should be equal to T3 and T2 is equal to 0. The thrust coming from this motor should be equal to 0. The tau 1 plus tau 3 torque generated by the motor 1 and motor 3 should be compensated by the torque produced by this particular motor, right? So think about it in a normal quadcopter, the individual thrust, sum of all thrust should be equal to the weight. Here we are talking about failure condition. One of the motor is failed, T4 is gone. If I am operating with a tricopter thing, then again the torque balancing will be difficult. So we make an assumption here, T1 and T3 together they will be able to take care of the weight. The T2 should be equal to 0, whereas the torque produced tau 2 should compensate tau 1 plus tau 3. Okay, this is a condition. If it happens, then the aircraft will be stable, right? Now that's the thing. Okay, can I produce 0 thrust? If you look at it, most of the aerofoil what we use, it's all symmetrical aerofoil. So we need a different airfoil itself to achieve 0 thrust, but there is some torque, right? So what we did is we again we go with the blade element theory, trying to understand how the thrust and torque is produced. You can approximate this, and we talked about it in the first lecture. The thrust produced is proportional to the speed square, and torque is also proportional to the RPM square, right? And then you have the CL and CD of the wing will come into the picture, right? What we want, if you take a symmetrical aerofoil, if you look at this blue one, which is commonly used airfoil in propeller blades, they all use NACA 006, right? But we wanted to use E63 aerofoil, right? It's an cambered aerofoil. If you look at the coefficient of lift and coefficient of drag plot, the cambered aerofoil will produce it's not symmetric, so this is a typical structure will be there. With that, what I can do is I can produce 0 thrust, but I can have a torque. Okay, but we have to manufacture this particular aerofoil. That's going to be a real challenge, right? So what we did, we designed this particular propeller, and the propeller has been fabricated in the lab, and what you see in the picture, this is a propeller that what we fabricated. First thing what we need to do, we need to test the whole system. What is the thrust that we are getting? What is the cambered aerofoil, how much it is producing, the torque that it is going to produce. I have to measure this information, thrust versus torque information. If I use a symmetrical aerofoil, what is the thrust? If I use a cambered aerofoil, what is the thrust versus torque? So we plotted this, right? So we give a measurement here. We made the bench design to calibrate this particular aerofoil and a motor to study for a different RPM, what's going to happen, what's the thrust and this, right? Now based on that, whatever the design we have done, we are looking for close to 815 gram. That's a maximum that I can achieve. 815 gram for a cambered aerofoil and 180 gram for a symmetrical propeller. So I'm looking at something to build with this system, right? Now I analyze at the zero thrust pitch angle, what's happening with this symmetrical aerofoil, what's happening with the cambered aerofoil, how my experimental data is, can I get the data, torque versus RPM. I get the differences and I got the data again, right. So this indicates I can use a cambered aerofoil, achieve the hover equilibrium without any problem, right. Now moment I know maximum thrust I can get, I can design the whole aircraft, right. But you see here I am using variable pitch aircraft, right, and I want to handle the fault tolerance also. Fault need to be detected, right. Fault detection and isolation is needed because you need to know which propeller has failed. Based on that you have to deactivate the other motor. What I meant is the other motor have to change to a condition where it produces zero thrust but positive torque. That torque can counteract with the torque produced by other two motors, right. So I need to know. So fault detection and isolation system comes into picture, right. Otherwise if you look at, it's a typical flight control architecture. I have a trajectory generator which generate my trajectory, and based on that I pass on to my position controller which takes a reference trajectory, and then this pass on to attitude controller. Attitude controller sends to, there is something called reconfigurable neural network based control allocation matrix. For a given thrust and torque, I need to know what is going to be the pitch of the propeller, what's going to be the RPM of the propeller. I want to get that data. So I have to get this information. So I have an inverse approximation. I am doing it here, which will also take the failure into account. Based on that it will tell you which motor have to run at what angle, pitch angle, and what is an RPM. So that calculation will take place. So this is my inner loop. Inner loop has an reconfigurable neural control allocation matrix. If you remember, in our regular control allocation matrix there is a 4x4 matrix for a quadcopter. Based on the torque and total thrust, it will give you what's the RPM required, right. That inverse function is already there. I can't do here because for every thrust I can get two values of RPM versus pitch, right. So I have to approximate this inverse relationship between the torque versus RPM and pitch attitude. Blade pitch, when I say here pitch of the blade, okay, not the drone ka pitch angle, it is the pitch of the blade I can control here. So I have to do this, right. So modification, what we have done, we take the command, we also have a small system here which will just take care of this neural network to convert, and then that will provide whatever the phi d, theta d, psi d dot required, and that will go in to find the RPM, right. So here for position and attitude controller we are using PID, same as what we described in this course, right. There is a fault detection isolation, it's there, right. We have not really implemented. Instead what we did, there is a time it will take to identify the fault, isolate that particular motor, and that information to get that information it will take approximately 50 milliseconds. There are research articles talks about different mechanism for fault detection. One can implement that. It will approximately take 50 milliseconds to process the information, identify and isolate the failed motor, right. So what happens, I get to know what is my moment and force, that is a total thrust, and I pass on to my control allocation matrix along with this failure. So I will get to know two values, RPM and pitch attitude. If you look at a normal quadcopter, it will give only RPM, if you remember in our earlier slide. Here is a variable pitch quadcopter. I can change the pitch of the propeller as well as the RPM. So I have two values for all the 4 motor and propeller system. Right? There are 2-step approach. First, we get the individual thrust and torque. We calculate that. What is the individual thrust and torque? Right? So we will compute Tx, Ty, Tz, and then total thrust as an input. Then we will get contain 4 individual thrust forces. M is the index of the failed motor. With that, we will just get only the individual thrust forces what we are looking for. Right? So basically, what happens? T1, T2, T3, and tau 2. Let's say the second motor failed. So this is how the equations are. In a case is 4 motor fails. This is how it converts that to a required torque and thrust into T1, T2, T3, T4, and then from there we can compute what should be the tau 2. We can get from that particular opposite motor with 0 thrust and solve it. We can have an algorithm like this which can solve it. Right? The part 2 is I am instead of I give the omega. Right? I will try to get the given the tau d and phi d, I can get the omega d. Right? What is the thrust required from that particular motor? What is the pitch of the propeller? I can find out what should be the omega d. Right? So I am fixing the pitch because I know how much torque I need. For that torque, what is the pitch of the propeller will provide 0 thrust and that particular torque value. That is the pitch I am fixing and sending the total thrust requirement alone and finding the omega d. Right? So it's basically if you look at, I can do a wind tunnel test using this particular motor propeller system, collect the data for a different RPM, different pitch. I can approximate the inverse function of this neural network. Then I give the thrust and the pitch, get the RPM value. So I can do the inverse and I use this information to compute my omega. Right? Once that's done, what I am going to do? I am going to set the known pitch angle for the 2 opposite working propellers, and omega d is coming from my neural network. Right? So I can do this very fast. Right? So I can get these things very quickly if I am trying to do whatever is failed motor, if I am trying to say what is my lambda versus pitch, if I am trying to plot. So I can achieve this stability very, very fast. Right? Okay. The most important part, how do we realize the variable pitch? Right? So the motor is there, and then I have one servo motor here which controls the pitch of the propeller, and then I have 4 link system. So this is how it happens. The servo trying to move here. So if you see the link 1 and eta 1 is the torque that I can get link 2, and this is link 3 and link 4 which connected to the propeller blade. Right? So I have a 4 link system. To just realize this, I am trying to show here. The link 1 is connected to my servo which is connected here. Right? See here, this is a servo I am trying to connect. The servo crank is connected here. That will control the link 1 which go all the way through the motor. Right? And then I have a link 2 and link 3 and link 4. Link 4 is actually connected to the pitch of the blade, propeller blade. Using that I can control the pitch of the blade. Right? It's a variable pitch mechanism built. It's a 4-bar chain system. It's a very lightweight. It's about 8 gram. Right? And motor weight is about 47 gram. Right? So we have pins for linear motion control and rod, and all this is being designed in such a way that the vibrations are minimum and all this. Right? Okay. So it's actual VPP what we have fabricated. So this is the variable pitch propeller system. Here you can see the actuator clearly. This actuator controls the pitch of the propeller. Motor RPM is controlled here. So I can control pitch as well as RPM for every motor. Okay. So you can see I am moving the actuator. You can note down here. You can observe here, when I move this actuator, I can control the pitch. I can control RPM as well as pitch both simultaneously. Now we have the parameters of the propeller. We need to measure what is the propeller pitch angle that we are getting for a different actuator setting, because that's very important, right? We have to calibrate the actuator. If I give a certain input to servo, what's the angle that I can get? So we need a setup. So we looked at different the 4 link lengths, all that information. Based on that, what is exactly the pitch angle that I can get? We measured it in the lab. Okay. So we did the theoretical calculation. We also did the experimental data to understand what is the exact pitch angle that one can get for a different servo angles. So we did the plot to show the calculation of theory and practice more or less matches, except at the extreme angles. If you look at a minus 40 degree at plus 30 degree, there is a variation in between the theoretical and experimental, whereas in the range between minus 30 to plus 20, more or less it matches, right, for the pitch angle that what I can get. If I am trying to plot PWM width versus pitch angle, so again I am trying to plot to give an experimental, so I am trying to do the linear fit so that I can use this information directly control my pulse width, so that I can control my pitch angle directly, right. Same things we did for servo angle and PWM. So we did all the analysis, experimental versus theory, to validate, and then using the experimental data we did the linear fit, and then using the relationship we can see that the pitch angle gamma degree one can achieve with 0.09 gamma minus gamma naught. With that I can get the what is the pitch required for the particular servo, right. So we have now designed the propeller, designed the actuator mechanism, and then we did the experimental study on understanding how the RPM is affecting my thrust, how the servo RPM affects my pitch of the propeller. I have all the data. I made the approximations so that I can get the relationship, right. Now we need to design the whole quadcopter, right. So I decide go ahead with the quadcopter. I am trying to give the typical box like structure. We provided the additional, typically quadcopter will have 4 arms alone. So we have provided additional bar because you have a variable pitch here. The variable pitch started providing a vibration in order to minimize the vibration and reinforce the strength of the quadcopter. We have added additional 4 bars which provides necessary stability. So again, component wise we are looking at the weight, the motor's weight, variable pitch mechanism's weight, the servo motors what we are using, that weight, propeller blades, airframe, battery, electronics and wire. So if you put all systems together, the total weight is about 626 grams. Okay. Now let us look at the propeller. Typically this is what this is a propeller built for this helicopter, heliquad. It is a cambered aerofoil, you can see it here, right. It's a and then we use STM32 based autopilot. So if you see here, control allocation block is not a simple matrix which I can just use it and compute. So I have to have a neural network which approximate this relationship, right. So MATLAB has a very specific feature. I can design the entire controller including modeling and simulation in Simulink and tune the controller in Simulink itself. I can connect the Simulink block directly to Pixoc or any STM32 based autopilot flight control core. I can download the controller directly into my core and execute that file directly with respect to sensor. So that is the advantage of this course. In the course we talked about what are the sensor we are using, how we can model the sensors and complete mathematical model of dynamics of the quad, which we can write it in Simulink, and then once you have it, design the controller, and once you do the controller you can directly download the controller from MATLAB to any STM32 based flight controller, right. A Pixoc you can do it, Cube Pilot also you can use, you can download directly onto the Cube Pilot. Okay. So we did again to make sure what is the center distance from the center to chord length. So we did the calculation and we just computed how much is the distance from the center to the chord length, and we have the data with us, right. Now once the controller is done, there are two aspects why we designed this particular quadcopter. First, we wanted to see whether we can do mid-flight flipping. Means in mid-air I wanted to reverse the thrust direction, right, such that the aircraft can spin, right, and fly upside down. Again you see, you have to implement the controller. This cannot be just simple PID is sufficient to get your attitude. This control allocation block to get this need to be implemented. Again we use a neural network. You remember I showed you there is a relationship for a torque and a thrust. We have two input, RPM versus pitch of the propeller, right. So we did the inversion, given a thrust and a torque, what is the RPM and pitch needed, right. When we do experiment, given an RPM and pitch, what is the thrust and torque we can get, right. So we did the inversion, model inversion approximation using neural network, and we implemented that controller in the PICSOC STM32 itself directly using Simulink, right. So here this yellow background donates the inverted flight, whereas the white donates the normal flight. So just to understand what's really happening between the set point and actual value, right. So the roll and pitch what we are getting, how much is the error we are getting, we are just representing here. Sorry, the video there is a problem, it's not playing, I will play it later. So again I can do the mid-flight flipping. Now can I get the fault tolerancy? If you notice the propeller 4 here is supposed to in mid-flight we will turn off this propeller. If you turn off this propeller, I still should be able to get the necessary attitude control without the aircraft being spinning. Can it come and land smoothly on the takeoff platform, and can it sustain the flight and complete the mission without losing attitude tracking performances, right. You can see here. So the aircraft is taking off, right, and I am flying here. So soon you will see I will turn off this propeller. Propeller is in red. You can see now the propeller is turned off. This particular red propeller is turned off. I am still able to get sustained flight without spinning. I can complete the mission and I can land without one propeller, right. I can achieve the complete attitude also. That is the biggest advantage when you are using variable pitch propeller system, right. So you see moment you incorporate the controlling the pitch of the propeller, you will be able to achieve sustained inverted flight, and you can also handle failure, right. So one can also try morphing based drones. Suppose you are operating in a cluttered environment, right, where the environment requires lots of small spaces, or you are doing inspection in tunnel, inspection in pipes, or you are operating closer to look at the health of the pipes or the poles, or if you are in harbor, if you are looking at the crane's health you wanted to monitor, you are going through a small constrained spaces. In such spaces, when you want to fly, you can't keep the same shape. Can you change the shape of the propeller, shape of the drone while going through the cluttered environment? That is another way of looking at, right. Or can you do the flip? Can you do even when you are operating in those kind of environment, there is a high likelihood you may lose one of the motor propeller system. If you lose one of the motor propeller, is it possible to have sustained flight? You can complete the mission, right. These are the questions. with this course you will be able to model, you will be able to simulate, develop the controller, trying to understand the relationship, and you can synthesize your design, get the experimental data. You can plug in the experimental data, this RPM versus thrust information into MATLAB, right? And you can design the controller appropriately, which provides a necessary tracking performance. Once you do it, you can download the controller directly into Pixar, right? That is possible. I am not showing the autonomy aspects of it. I am just only highlighting what possible up to the control. Point-to-point navigation you can implement. Autonomy is a bigger challenge, right? To do autonomy you need to understand lot more, okay. Maybe I will just give you more details about what will happen if you are trying to implement under failure, right. If you just see here, when the motor fail, right, the green is a nominal and this is a failure zone, right. I am assuming for 50 seconds I am not getting any data, I am not sure what is happening to the system. Once I get which motor is failed, you see it is able to pick up and track both pitch angle, roll angle. It is also able to do a yaw rate. See, if you notice here, yaw rate goes very high the moment there is a failure is injected. After that period where fault detection is done, yaw rate brought back to 0, right. And you can see that theta dot as well as phi dots are all closer to 0, right. So, if you look at the RMSE error at the failure, roll pitch angles, they are all very small, yaw rates are very small, even if you include this particular region to compute, right. So, you can achieve necessary performances and you can design the system accordingly. And if you want to understand more about the work what we have done, you can refer to this particular paper, we will talk more about it, okay. Now, we are coming to the end of the course. I just want to give a summary of the course, right. So, what we did in the beginning, we started with basics of drone, how do you operate the drones, type of drones, and then we brought into 5 different modules. The module 1 talks about drone simulation itself, what is rigid body transformation, and trying to get the drone 6 degree of freedom model. Once you have the 6 degree of freedom model, can we realize that 6 degree of freedom equations in MATLAB, right. So, to do that you have to characterize your motor propeller and get the data, and with the data you can design the drone, you can identify the length and whether you are flying in X configuration or H configuration if you are using Quadcopter. Based on that you can do the design. We talked about all those realization in the module 1. Module 2 talks about sensors, right, intrinsic and extrinsic. Intrinsic is more like your IMU, inertial measurement unit, right, your accelerometer and gyro, and your altimeters that you could have. It could be petard tube or you could LiDAR or radar to get your altitude, and that will help you to get the basic states of the system, right. Then we talked about EKF, extended Kalman filter based sensor fusion, and estimate the states, right. So, you can get X, Y, Z, phi, theta, psi, velocity, and both translational and rotational states you can estimate directly with the sensor fusion. Then we talked about extrinsic sensors. Those sensors help us to understand the scene. It could be a camera, monocular camera or binocular camera, right. So, it will give you the depth, or you can have a 4D radar or 3D LiDAR which can help you to sense the context in which the drone is flying. If you talk about autonomy, you need to know more about the context. Where is the obstacle? Is there an obstacle? Where is it? Is it static? It is moving. If it is moving, at what speed it is moving, in what direction it is moving, all that informations are required for you to do navigation purpose, right. Then we moved on to drone controller. Again we realized different sensors in MATLAB. We showed you how to realize the sensor and span it in the simulation world. Then moved on to controller. We talked about classical as well as modern, right. We took a simple quadcopter, we we looked at the state space representation, and we talked about full state feedback design, right? We talked about yaw control, right? So we also looked at PID design, and then we have a MATLAB based PID tuning algorithm for specifically for drone attitude control. We explained that, right? From there we moved on to very important topic on drone navigation. The first thing in drone navigation is scenario generation. How to generate a scenario, right? How these systems are connected with the ground control system or with the RC and all that, how we can simulate them in a simulation world so that we can understand. But if you are going to put in a particular obstacle, how to do it, and creating that scenario, we talked about it. Then we talked about global path planning, right? A star, right? Digital. So how do you do the global path? You want to go from one point to another point given the map of the world. Then we talked about local path planner, right? Artificial potential field and control barrier function. Can you guarantee the safety when you do local path planning? We talked about APF and CBF, right? Then comes a very important module, drone autonomy. First we talked about autonomous flight, right? What is different levels of autonomy that you can get. If you talk about solo single vehicle level 1 to 5, right? Each level means what a human effort will be, where human effort will be less. Then we talked about group autonomy too, swarm based solutions. We also introduced how to use neural networks, what is basics of neural networks and basic recurrent neural network, and how to use a recurrent neural network to estimate the states of the system, right? And you can use that state, fuse it with a Kalman filter, do GPS denied navigation. These aspects we discussed, and then we moved on to swarm flying, right? Group of drones flying together. What is a swarm? What are the challenges in swarm? We took at examples of how they can combine together to do firefighting, right? Now the last lecture in the autonomy, we talked about advanced drone design. I took an example so that I can define the requirements. Based on the requirement, what kind of design is needed, how to do that, and how to fabricate, collect the data. We didn't go in details of fabrication, how we did the fabrication, collected the data, how we approximated the relationship, and we used the neural network and implemented in the drone to highlight that how this course could be used. Using the design requirements, you can plan, simulate, and directly download that, right? Now, if you ask me after finishing this course, I still want to be an expert in UAV technology, what I need to do, right? You have to take courses on flight dynamics so that you can strengthen yourself, because what we covered in this particular course is multi-rotor system. You have VTOLs, vertical takeoff translation vehicles, and you have fixed wings. So you need to understand, and when you are taking VTOLs, vertical takeoff and translation, the transition phase is really challenging, and you have to understand the dynamics of the transition phase and to design a controller so that you can design and implement and validate the typical vehicle. So you need flight dynamics definitely, and you also have to take a course on path planning itself. Path planning, they will be covering more on simultaneous localization and mapping, particularly on navigation aspects. See, guidance aspect will come into picture. They will be covering more details about it. So you need to know how do we navigate, how do we localize yourself if you don't have. Suppose if you are operating indoor, GPS is not available. How do you localize? What are the different mechanisms available to localize yourself? Because autonomy requires those informations. You will be getting knowledge when you take such courses. Of course, AI is very important, right? AI is used in perception also. AI is also used in control. So I showed an example how we use AI for GPS denied navigation alone, how we use AI for advanced drone control system itself, right? But if you get into deep learning, image is a sensor which is trying to help us the context. So you can use aerial perception itself to understand, because we don't use only image, we use sometimes radar and LiDAR. So I wanted to call as instead of visual perception, I am calling it as aerial perception, which has a multimodality. How do you use this modality to understand the context in which the drone is flying? Another important skill you may have to acquire is a reinforcement learning, because today the new age solutions are moving directly into action, right? Sensing to action, and without being explicitly told how to fly. There are recent works where people talk about, can I have a single controller which will work for multiple drones, right, of the same class, right? A typical quadcopter, if you take same controller, should work for a quadcopter which carrying 1 kg payload, quadcopter carrying half a kg or 2 kg, 3 kg. I don't want to redesign the controller. Can you come up with reinforcement learning based policy which works for multiple drones, right? So reinforcement learning is very important when you go into swarm and all that, right? So RL is another skill is required. SLAM is very important, because when you talk about integration drone into cluttered operations, localization is very important, so you need to go through that. At the end of the all these courses, very important, embodied intelligence. Basically all these intelligence are fine if you say I am going to run all this in a big system. We know we have a limited power, limited weight, right? I should be able to implement all these intelligence onto a small edge devices. Not just implementing on edge devices, they have to operate at certain frequency. What I meant is, if you are going to sense it and you say every 2 seconds only I am going to give wire as obstacle, think about it, what is the implication it will have in control. Usually our inner loops operates about 50 hertz, our outer loop operates in 5 hertz, right? So we need to get the context understood at least in 5 hertz. If I can understand in 50 hertz, it is much better, because I can be more precise and accurate, right? So embodied intelligence is a very important skill one need to acquire if you want to be an expert in UAV technology. Right? That's one part of it. The other part of the course, I am just looking at what else I can do. Having done this particular course, can I try something? So I thought I'll just list you some projects that you can try. Vision based obstacle avoidance. You know APF, right? Artificial potential field. You know CBF also in this course. If there is a camera, even you can take a stereo camera, right? The stereo camera can tell you the depth, relative distance between the drone and that obstacle. Once that information is known, can you implement the artificial potential field so that the local path can be generated, right? We know APF will not guarantee safety. Can you formulate a control barrier function and generate the path so that it is safe for the drone to navigate, right? So you can try that. Soft landing and precision landing. Suppose if you put a camera vertically down, right? I can use a Aruko marker to identify where I have to land, and you can be precise on top of it. Again, the challenge will come when the drone comes closer and closer, the bigger Aruko marker vanishes. You have to lock onto a smaller one to just make sure that you are precise. Soft landing is very important. My descent rate currently for all the drones are constant, right? I come down at 5 meters per second, even if you are at 200 meters, that's not the soft landing is, right? You have to come down when you come closer and closer to the ground, the rate at which you are descending should be exponentially decreases. When you exactly touch down, the descent rate is 0, right? The height between the ground and the drone landing gear should be greater than epsilon. The error should be greater than epsilon. Epsilon is always a positive small number. Can I get the soft landing, right? That you can try. Tracking the trajectory, that is very important. We talked about PID based control and state feedback. One important skill I forgot to mention, that skill is advanced control, right? Advanced flight control course you should go through, right? So that you can try to understand what are the other techniques for controller design is available. One such approach is model predictive control. Can you use a model predictive control to track the trajectory accurately, or can you implement other advanced control techniques for tracking the command as accurately as possible, rejecting the disturbances more efficiently, right? Control is a very important skill. You should take a formal course in control, right? Both classical as well as advanced, modern control, looking at advanced controller designs like LQR, LQG, right? Linear quadratic regulator, right? So model predict, these are very important because at different point of time when you want to work on a specific problem space, your requirements differs. The classical control design may not be sufficient to achieve. So how do we do that, right? So we have to look into those skills and apply here. You can also start thinking about advanced control, advanced drone design itself, right? So like what I mentioned, morphing, ducted fan based Y propeller and motor propeller system, can you work on ducted fan, right? So you can look at various propulsion systems and how use them to get the desired mission performance to be done, like what we have demonstrated in the last lecture on variable pitch propeller based drone, right? Or even you can look at application domain space. For example, if we take a logistic drone, right? How do you design the drone and how do you put the payload? Moment you put the payload, right? Payload could be 5 kg. 5 kg means what is the volume that you are talking for 5 kg. That volume will introduce some performance variations, right? So how do you handle it? Suddenly I want to drop 2 kg down, right? Now how do you balance my weight? How do you get my controller designed for that particular scenario? That's an interesting problem altogether, right? I can do the drop. Think about it, I'm using this for such and rescue mission. I want to have 4 payloads I'm carrying, 4 packets of survival kit. I want to drop it to 4 survivors, right? I dropped 1 kit, each one is 1 kg. Now 3 kg is there. How do I get the stability in my system, right? Because the weight is no longer balanced, my CG shifted slightly. My moment of inertia may not have, if you put it in gimbal it's okay, but still how do you design that? How do you take the control aspect of it? So that's an interesting problem altogether. If you combine this course and if you are an expert in AI, then you can look at how to use perception itself, right? To handle object detection, tracking, then you need to estimate the latitude, longitude of the target, and then you have to maintain a certain distance between the target and the drone. How do you do that? Coordinated tracking, right? So those things, interesting application use cases comes into picture. Agriculture again, quite an interesting space where if you talk about precision agriculture, can you monitor the soil, right? How the drones can fly, collect the soil data and identify real-time growth, and then getting the image and get a 3D reconstruction done from perception, and using the reconstructed world, can you identify what is the volume of production, so on and so forth. There is a huge possibility of projects in the application space. I'm just not listing everything, I'm just highlighting few which you can try it out and experience, so that whatever you have studied, if you try to implement, you will get more confidence. Okay. With that, I wish you all the best and looking forward to see you in other courses in next year. Thank you.